In this section, we look at sampling distribution of a sample mean. That's a probability distribution of all possible values of the random variable x bar now, the sample mean, computed from a sample of size n from a population with mean mu and standard deviation sigma. This is a little bit different, it's kind of awkward, and we have to let it settle in for a moment. But what happens is we have a regular distribution, like this one that's normal. X values are approximately normally distributed here with a mean of 77 and a standard deviation of 11.25. I used these values from the scores from the midterm. They were approximately normal, mean was 77, standard deviation of 11.25. Now that's for all 40 exams that were returned, so that's a population. Now if I were to take a sample from this population, let's say a sample of size 5, and calculate the mean of that sample, then I have a new value, a sample mean from a sample of size 5 from this population. Now let's say we put them back into the population, mix them all up, and then draw another random sample of 5 more students and average their exam scores. If I do that again and again and again until I have all possible sample means, so I've taken every possible sample of size 5 from the population of 40, I can then make a distribution on the sample mean. So I'm not talking about the exam score itself, but the average exam score for 5 students. The result there reduces the variability, because if you think about your low or high exam score now being averaged with 4 other students who probably are closer to average than yours or closer to the mean, then that low or high score has less of an influence, which means it has a lower variability in general. So that distribution, which was normal in the blue curve, becomes the green curve. We call that the sampling distribution for sample mean x bar. This one in particular is for sample size n equals 5, and the thing that changes is the standard deviation. You notice that the mean is the mean. The mean of the sample means is still 77. If I were to average all the means of size from sample size 5, I would still get an average of 77. The mean is still the mean. The middle is still the middle. The center is the center. The standard deviation, however, has been affected. It's reduced. It's reduced in a very finite way. We know exactly how it's reduced. It's the standard deviation of the distribution divided by the square root of the sample size. Larger sample size, less variability. For us, we would have 11.25 divided by the square root of 5 for a new standard deviation of this distribution of sample means of 5.03, if you like. So we reduce that variability. Now you notice that we drew from a normal population, so we probably aren't too surprised to see that I drew a normal curve again in green, because if the x variable is normally distributed, we would expect the sample mean to also be normally distributed. That's not mind-blowing. However, the central limit theorem tells us that no matter the shape of the underlying population, so if the underlying population is uniform, like this, or the underlying population is skewed to the right, or even skewed to the left, the distribution of the sample means becomes approximately normal as the sample size increases. So that's an interesting theory, and it's well represented by this visualization from Brown University. So alpha and beta control the shape of the distribution there. When they're equal, we had uniform. Oh, can't do it again. But we can determine how many like the size of our samples to take and how many of those samples to take. So let's say we're going to take 5 samples of size 100 from here. maybe. Okay, so that's one sample of size 10. Let's say we would like to take 10 samples of size 10. The computer visualizes what happens. It randomly selects 10 items from this distribution and does that 10 times to get the following distribution. But as the number of times that we make these samples increases, we can see that the resulting distribution becomes closer and closer to normal. 50 samples, 80 samples of size 10, the histogram is getting closer and closer to normal. If we have 100 samples, and the biggest sample size the computer can handle was 15 from this distribution, we see normal, and we were basically started with a normal or a uniform distribution right here. As we move alpha and beta, we can make kind of a crazy distribution. So we haven't even talked about this guy specifically, but what if we let our distribution look like this? And we take a few samples, so let's do 5 samples of size 5. So there's 5, they do it 1, 2, 3, 4, 5 times. Doesn't look approximately normal, but as the number of times we make these samples increases, we see that the distribution, the frequency histogram there, gets closer and closer to normal. So if I max it out at 100 samples of size 5, almost normal there, still skewed a little bit left, but what if our sample size is larger, like 10? Skewed left a little bit still, sample size 15. It's getting closer and closer. I'd say there we've hit the approximately normal curve. Now we can play around with this, change alpha and beta, there would be your normal distribution. This guy, maybe he's skewed to the right now, kind of funky little curve. There's really skewed right, but if we take enough samples of large enough size, the distribution will be normal. That's an odd thing. The great thing for you is that it means that we always can make the same conclusion. For the mean and the standard deviation of a sampling distribution, first we notice that it is approximately normal all the time, regardless of the underlying distribution. The mean of the sample means is the mean of the distribution. That's not surprising. And then the standard deviation of the sample means is the standard deviation divided by the square root of the sample size. This here is the key to this section. It's the only adjustment we have to make, the only new thing. It's what happens when you see the probability of x bar doing something less than, greater than some value, whatever it is. When we're talking about sample means, we need to make this adjustment in the standard deviation, and then the rest of our calculations will be correct. We'll use the same table, all the same processes. So here we can make our z score. It's the x value minus the mean divided by the standard deviation of the distribution, but now that standard deviation of the distribution is divided by the square root of the sample size. So when you put it in the calculator, make sure to use parentheses as I've indicated here. Now let's try some examples. Pretty boring example, just get all the facts. A random sample of size 36 is obtained from a population with a mean of 64 and a standard deviation of 18. The sampling distribution, regardless of the underlying population distribution, is approximately normal. We saw that from the central limit theorem. Sample size is 36. The mean of the sample means is the mean of the distribution, that's 64. And the standard deviation of the sample means is the standard deviation of the distribution divided by the square root of the sample size. Standard deviation of the distribution is 18. The sample size was 36. So we have 18 divided by the square root of 36, also known as 3. And you see how much that variability was reduced. Once we know key facts about the distribution, and here we know that it's normal, the mean is 64, the standard deviation is 3. We can find probabilities associated with the distribution. The probability that x is less than 62.6 needs to be converted to a z-score. just like we did in section 6.3, and then from the z-score we'll look up the area in the table. The z-value is the x-value we have, subtract the mean, divide by the standard deviation, and because we're talking about sample means, we divide it by the square root of the sample size. So you could even say your x-value is an x-bar value. So here we would have 62.6 point of interest minus 64 given mean, divided by parentheses standard deviation of 18 square root of 36, end parenthesis in your calculator to find a z-score value of, I get negative 0.466. Of course, the table goes to 2 decimal places, so look next door to that 6 and you see that you need to round up. So now your probability is, what's the probability z is less than negative 0.47 to 2 decimal places. The picture, remember, approximately normal. The mean is 0 of the standard normal distribution. Negative 0.47 is to the left of 0. And we want to know the probability z is less than that, so we want the area to the left of negative 0.47. That's a simple read from the table directly of negative 0.47. Read right away that it's 0.3192, and that is the probability that we find a sample mean less than 62.6 from this distribution.